So in the last video we have seen what are metroids, and how we have also said that this will give us a framework to work with the greedy algorithms. In this video we will see one problem in the context of job scheduling. Let's get into the details. So let's consider the next problem. It's in the context of job scheduling again. So you're given a set of unit jobs. In other words, every job requires 1 unit of processing, and so you can think that this unit could be days or hours. It may be easier to think them as days, and each of the jobs have deadlines, right? So it's like an assignment. Doing an assignment actually takes 1 day of efforts, but each of the assignments have different deadlines, and there is a penalty. There is different weightages for these assignments, and if you don't do an assignment, or if you don't complete a job by the deadline, then you have to pay the penalty. Now the given set of jobs may be in such a way that you may not be able to schedule all of them, so you have to pick a subset of these jobs and decide when to do these jobs, so that the total penalty, right, so you will pay penalty for the ones that you are not scheduling. The total penalty that you pay for the jobs that you don't schedule is minimized. Okay, I repeat, every job takes 1 day of 1 unit of processing, and every job has a deadline. You have to schedule this job before the deadline, and so you have to pay a penalty for the jobs that you cannot schedule, right? So one such example is the this for a particular example, there are 9 jobs, and the maximum deadline is 7. So obviously you cannot complete all the jobs. So okay, you have to pick the penalty of the jobs are different. So if you change the penalties, you will get different solutions. So for example, if you look at this particular job here, it has a penalty of 25, and the deadline for that is the 4th day, whereas it has to be completed on the first day. If you can't do it on the first day, you have to pay a penalty of 10, and so on. So this has to be completed before the 7th day, and the penalty is just 2. So given a collection of jobs of this kind, each of them requires 1 unit of processing, and each job has a deadline, and you have to schedule it in such a way that the penalty for the jobs that you discard, that you end up not scheduling, is minimum. So what we are going to do is that we will try to map this into one of the problems of metroid. So what is a natural thing to do is that we have given a set of jobs which needs to be scheduled with deadlines. These collection of jobs will be S. Okay, now so if there is if we will consider the subset of job and ask the question whether this every job in this subset of jobs can we schedule it before the deadline, right? So that is a subset of jobs. I repeat, S is the set of jobs that are given to us. Yes, a subset of job is said to be independent if all the elements in all the jobs in the independent set can be scheduled meeting all the deadlines, right? So for example, if I take the entire set S here, you cannot schedule all the 9 jobs because the maximum deadline is 7, so obviously you cannot. But if you discard let's say this job and probably this job, the rest of the jobs can be scheduled. On the first day I schedule this, and the second day I schedule this, on the third day I can schedule this, fourth day this, fifth day this job, sixth day I can schedule this, and seventh day I can schedule this. So if I discard 2 jobs, then whatever set that I get, there is a valid schedule for the rest of the jobs, and that particular set is said to be independent. A set of jobs is said to be independent if all the jobs in this set of jobs that you picked can be scheduled meeting all the deadlines. So the base set is the given set of jobs, and the independent set is a subset of jobs which can be scheduled meeting all the deadlines. The claim is that it forms a metroid. So in order to show that it's a metroid, then we have to show three things. One is that empty set is an independent set. That's trivial, because if you don't give me an empty set, all the jobs in the empty set can be scheduled meeting all the deadlines. The other property is that subset of an independent set is independent. That's also easy to see, because if you can give me a valid schedule for some of the jobs, and if you knock off some of these jobs, right, so you can easily see that you can retain the old schedule. After you delete some jobs, if the original set of jobs, it was possible to schedule all of them meeting some deadlines. If you delete some jobs, it's still possible to schedule all of them meeting all the deadlines. And the last property, that is the exchange property, that is the tricky one. So we will look at the formal proof of why the exchange property is true. So we given a set A of jobs which are independent. There is a set B which is also independent. Now we want to show that there is an element in A which is not in B, but I can schedule that one job which is in A which is not in B along with the jobs of B. Let's look at a schedule for A, right? So this is the schedule for A, and the below what I have written is the schedule for D. So all of them are unit jobs. This is on different days, and this takes exactly 1 day, right? The first day, these both the schedules are doing one job. Since the number of elements in A is greater than B, there has to be a day on which A is doing something but the B is not doing anything, right? So since number of jobs scheduled by A is greater than the number of jobs scheduled by B, there has to be a day on which A is doing something and B is not doing anything. So we can easily shift this particular job to this location. The only problem in the proof is that this particular job may be there in the collection B. So the B may be doing it on some other day, right? So if this job on which A is doing something but the B is not doing anything on that particular day, and if this particular job that is under consideration is not in B, then I can easily shift this to B, and that basically means that you are adding an element into B which continues to be independent. But if this job is in B, then we will go and look at a day on which A is doing something, right? So then again, so what we do is that we move this job to here, right? Since this job is same as this job, but instead of doing on this day, he is doing in some other day, we can always take it back, because A is doing on this particular day. So the deadline of this particular job, which is X, is certainly smaller than is certainly greater than equal to this day, because the schedule A is this particular job is scheduled on this day. So B also should be able to schedule it on this particular day. So we will move this job from here to here. So now you see that on this particular day A is doing something but the B is not doing something. So there has to be this, if it is there in the collection, maybe it is there here, then we move it to here and apply the same argument again. So because I got a day on which A is doing something but the B is not doing anything, right? So if you keep exchanging, there may be at most the number of exchanges cannot be more than the number of jobs in B, because every job in B can be exchanged at most once. So the total number of exchanges will be at most the number of jobs in B. So at some point of time, our algorithm should stop with the condition that on a particular J, A is doing something but the B is not doing anything. So and this particular job which A is doing on that particular day is not done by B on any other day. Okay, in that case you can move that job to B and still schedule, we should still have a valid schedule for B. This proves that the exchange property is satisfied. If the number of jobs in A is greater than the number of jobs in B, we are able to figure out a job in A which along with the jobs of B can be scheduled, right? So and the job that we pick is not in the collection of B. So now we have a so the given so we are able to map it to metroids. Now we have to see how this the greedy algorithm that we defined for the metroids can be used. So we want to minimize the penalty of the jobs which you are not doing. This is equivalent to maximizing the penalty of the jobs that are scheduled, right? So this can be called as gain, though it need not be called as penalty. But if you so what you want to do is that you're going to pick a few jobs and you're going to discard few jobs. So the original problem was to minimize the penalty of the jobs that you don't that you end up discarding, right? So which is same as so if you just count the sum of the penalty of the jobs that you end up scheduling, it's equivalent to maximizing the penalty of the jobs that you schedule. So the greedy algorithm that we defined for the metroid says that you consider the set of jobs in the decreasing order of the deadlines and schedule them schedule them. See whether this can be scheduled with the set of jobs that you have already picked. So I have one more line here. So we want to decide whether this can be, when you consider a job in the decreasing order of the deadlines. So what we do is that we want to see whether a new job that is coming in can be scheduled along with the other jobs, and even if it can be scheduled, when do you schedule it? The policy that we are going to consider here is that if it is possible to schedule it as late as possible, right? So you consider the jobs in the decreasing order of the deadlines. That is what the greedy algorithm says. But I want to know whether it can be scheduled or not. If it can be scheduled, then when do I schedule it? So that's why I have an additional line here. If it is possible to schedule it as late as possible, right? So why is this as late as possible? It will always give a valid schedule. If it is possible to schedule, then this particular policy that I have, which is the as late as possible, should always schedule, right? If there is a so given a set A, what we are saying is that so this was applied, we applied as late as possible solution on this, and there is a new job that is coming in. Now if I apply, I also want to see whether this can be scheduled or not. That means that if it can be scheduled only if before the deadline one of the day was free, right? So if all the days before this deadline are all occupied, then A union X is not independent. So what all that I need to know is that before the deadline of X, is there a day on which I can schedule it? Is there a free slot available on which the A none of the jobs in A actually are scheduled? If that is possible, then it is possible to schedule. Now we will see why as late as possible will actually serve the purpose. If it is possible to schedule using the as late as possible, then clearly there is a valid schedule, right? But if the as late as possible schedule says that it's not possible to schedule, then if you look at the deadline of X, and all the jobs, all the days before that have been occupied, and all the jobs which are scheduled before the deadline of X have been scheduled as late as possible. That means that none of them can be rearranged to the or moved to a later date, because all of them have been scheduled with the policy that they have been scheduled as late as possible. So they cannot be, none of them can be pushed to a date after the deadline of X. So if there are all the dates before X, deadline of X has been already taken, that means that it's not possible to schedule X. Because if I have to schedule X, I have to push one of the jobs which have been scheduled before the deadline of X to a later date. But none of that is possible, because all the jobs we have scheduled based on the as late as possible. So this proves that if I just follow the as late as possible, I will know whether A set is independent or not, right? So when you want to add A union X, so what the way we are going to implement is you can imagine that there's an array of days, and initially everything is going to be 0, And so we want to know whether on a particular day is free or our schedule has actually scheduled something. We'll have a boolean array. Initially everything is 0. 0 means that none of the days are occupied, and when I start allocating a job on a particular day, particular slot, I'll convert this into 1. So here you notice that the 2nd, 4th, 5th, 6th and 9th slots are already taken, and the remaining slots are free, right? The free slots are marked by 0, and the occupied slots are maintained by 1. Okay, so when I if the deadline of a job is let's say 6, then there is 2 slots on which it can be scheduled, right? So we can go and schedule it there. But if I put something on 1 and also put something on 3, then if you give me a job whose deadline is 6, all the slots are occupied, so it cannot be scheduled, right? So it's easy to if you follow the as late as possible, if there is a valid schedule, you can always figure out whether there is a valid schedule or not. In other words, the independent set can be answered. Now, how do I implement this? One of the brute force way of implementing this is that given an I want to keep going back till all the numbers are 1. The moment I get a 0, right, so I want to conclude that this is the place where I am going to insert it. If all of them are 1, then I am going to return -1. So if I return -1, that means that all the dates before the deadline of the given job are all occupied. In that case, this X cannot be scheduled along with the other one, so it has to be discarded. So if I have to implement a brute force way of doing it, so I have to write some more condition here. While I is greater than 0, greater than or equal to 0, see if A of I is equal to 1, then I keep going back. When I come out of this while loop, if I is -1, that means that this job cannot be scheduled. If I is still positive, that means that A of I is 0 there, that means that on the ith day we have not scheduled any job, so you can schedule it on the ith day. So when you return this, if you get a -1, the job that you consider cannot be scheduled. If you get a index which is greater than or equal to 0, it can be scheduled on that particular day. So you turn A of I to be 1 from 0. So in order to answer every query whether I can this job can be scheduled or not, when you consider the jobs in the decreasing order of the deadlines, what you basically do is that you might, and if you look at this implementation, to answer every query you are starting with that index and keeping going back till you find an empty slot. This can be in worst case order n. In other words, the f of n that we described in the is independent function can be as bad as order n. So the sorting the jobs based on the deadlines takes order n log n plus n into this single iteration can take order n time. So the entire complexity of this algorithm can be in worst case omega of n square. Right, so but this is not the best way to do. We can't do anything about the sorting. This will be n log n. For the second question, answering the question whether there is a empty slot vacant before the deadline of the given job, right, that can be answered efficiently using a balanced binary search tree. So this entire algorithm can be implemented in n log n using a balanced binary search tree. In the binary search tree that we are going to consider, the search index, the search property is maintained based on the index of the array that we just described, and in each node, in addition to the search key that is the index, we also keep track how many number of nodes which are there in this subtree and the how many free slots available among all the days in the subtree. Right, so using these two additional information and doing some clever operations on the this particular binary search tree, we can answer this question. Given a I, whether there is anything which is free before this deadline of this particular job, and even if there is one, we have to find the day on which it has to be scheduled with the policy that I want to schedule it as late as possible. That means that given a I, I want to go back and get the first index which is 0, right? So this query using the binary search tree can be answered in log of n. So the total complexity of this algorithm will be n log n for sorting plus n into each query, whether the job can be scheduled or not, and if at all it has to be scheduled, when to schedule it, can be answered in log n using the binary search tree that I just described. So the entire algorithm turns out to be n log n. I will leave it as a homework to figure out how to write the algorithm for how to use this details of the balanced binary search tree, so that you can implement this in n log n. So in this video we started with a job scheduling problem, and then we mapped it to the metroid framework, and we showed that it's in fact a metroid. So once you defined that it's a metroid, then we straight away got an optimum algorithm to solve the problem, which is a greedy algorithm. So so the proving that the algorithm is correct reduces to the problem of proving that whatever mapping that we define from the given problem to metroid is in fact metroids. And the only other details that we have to figure out is how to write the is independent function efficiently. In the next class we will come back to more such examples of problems which can be mapped to metroids. One such specific algorithm that we are going to look at is Kruskal's algorithm to find the minimum or the maximum spanning tree.